So today we're going to start with our lesson. Let me open the slides again. So how are you? New week.
Is Dr. Fine, Alhamdulillah.
Fine. Anas, you're early this morning. So how about last class?
Good.
Right? Everyone is still sleepy because we start 15 minutes early. Is everyone okay?
Okay.
Okay. A bit sleepy, eh? A bit sleepy. I'm also sleepy. Last night I slept at 4. All right. Well, because that's what happened when we have these corona things, right? We don't take care of our sleep time and we sleep late. Share my screen. Yes. And before that, I would let's say sorry about last class. I couldn't attend the class, couldn't give a lecture, but I do give you an exercise on the previous topics. Okay, on the previous topics, where most of you are doing well, and of course there are some mistakes, and I will look into it one by one. What I'm thinking is to can you see my screen right now? I'm opening the compilation of answer.
Yes, Doctor, we can see it.
Yes, Doctor
Okay.
can.
What I'm trying to do is to compile all your answers. Okay, to compile all your answers and then correct where it is not quite correct. So I will write the correct answer here and then I will share with you. So the sequence that I am compiling here is by textbook questions. Okay? The question given to you was random, but I'm compiling in the sequence of textbook question chapter 2, okay, 2.1, 2.2, and so on. And then chapter 3, and then chapter 4, and then the past year questions. Okay, some of you also have trying to answer the past year question. I also have shared the past year question with you. I think check in the e-learning. Okay, there are 3 past year questions that I'm sharing with you, which is I think this is last year, 2020, 2019. And late 2019. The digital system is offered in both semester. So I only have 3. I mean the coordinator share with me 3 previous test 1 because test 1 is coming soon. So you can check the test 1. Check the test 1 like the format and what kind of questions he's asking. So like this type of question is given to you. So you can check the answer. So before if I'm taking some time to check all the answers, you can check your friend's answer. Okay, you can do it yourself and then check if your answer is the same with your friends. Right? So questions that are from the previous chapter given to you in the exercise except for the arithmetic circuit, which we're going to start taking the lesson from today. And you can see what kind of question being asked for each chapter. Pause.
So today's chapter is not covered.
Yes, today we're going to do the arithmetic circuit.
So until module 4.
Oh, okay. You mean the chapter. Okay. The chapter that is covered in test 1. Is that your questions?
Doctor, your mic is
Yes.
muted, I think.
Yes. Sorry, Ahmed. Anas.
I can hear you now.
Okay. Here, okay, we have done well, not really, because the first two is what you have done in digital electronics, so I skipped that part. And then we have learned the number system, and we're going to look the adder and the rest of the arithmetic circuit, and also the combinational logic design. So the test 1 will basically cover until the combinational logic design case study. But as you can see in the past year questions is basically asking until adder. Right? So we have, okay, we have,
So we can say it's until module 4.
I usually it's until
Or
4, but
module 5.
officially it's until combinational logic design. Okay. Officially it's until the combinational logic design, which is module 6. When we're doing module 5.
Okay.
Right. Okay. Ready, everyone? Okay. So today we're going to do the arithmetic circuits. So what are the arithmetic circuits? We have adder, subtractor, multiplier. We're not going. I think we're not going to do divider. But I'm not sure. But these are all the arithmetic circuit. Okay. And arithmetic circuit is usually a combinational circuit. Combinational circuit. Right. So in digital electronics, you have learned that we have two types of circuit, which is combinational and sequential. Okay. All right. So Ain Nabila here. Ain Nabila, tell me what is the combinational circuit compared to the sequential circuit? Ain Nabila? Ain Nabila? I said, Nabila, do. Okay, Aiman Najmi. Aiman Najmi.
Okay, Doktor.
Okay, Aiman Najmi. Apa combinational circuit? Combinational circuit.
Is a circuit that combine
Combine.
logic and logic.
Okay. And logic. Yeah.
I think that's all.
That's all. Okay, not quite right. Aminu, what is combinational circuit? Aminu? Right. So combinational circuit is a circuit. Of course, we can have any gates here inside here, but it's a circuit that rely only on the current input. From the current input, you can get the output. Okay? Like the adder, subtractor, and all the arithmetic circuit. Okay? But a sequential circuit is a combinational circuit that has input, output, and then it has a memory where the output will be saved into the memory and come as input. So sequential circuit is a circuit that relies on the current input and the previous output as the input. Okay? Right. So now we're going to see how the arithmetic circuit is designed. Okay. Arithmetic circuit is designed using an iterative design. Iterative, what does it mean? Bala Murugan. Bala Murugan? Bala Murugan? Sleeping, eh?
Sorry, can you repeat again?
Not Anas. Bala Murugan, eh? What is iterative? What is iterative? What does iterative mean?
Repeating.
Can't hear you.
Repeating.
Repeating. Okay. Thank you for answering that. Okay. Marco. But yeah, that's correct. Repeating. Repeating. Iterative means repeating. Or when you do a programming, you are in a loop to repeat the same process. Okay. Since arithmetic process is repeating the same process. For example, we want to add 1010 and 1111. Okay. In this bit, we change the pen. So we are repeating the same process on each bit. Okay. We are repeating the same process on each bit. Okay. At this bit, at the rightmost bit, we are doing adding input 1 at input 2. Okay. And then at this bit, and also the carry, if you care about the carry. At this bit, we are also doing input 1 at input 2 and the carry, and so on. So in the arithmetic circuit, each bit is repeating the same process or using the same algorithm. So a circuit, this is an 8-bit logic circuit, can be decomposed into smaller bit slice. We slice the bit by bit. Okay. Bit slice blocks to facilitate the design process. Okay. Remember your 4-bit ripple carry adder? Okay. So each bit is repeating the same process of full adder. Okay, full adder. So this is not 8-bit, 4-bit, it's an 8-bit. Okay. So that is the iterative design. Okay. Now let's see adders. So we have known half adder and already understand about the full adder. I'm not going to repeat this because you've done this several times, I think, during the first year, and then in milestone, and then in lab, unless because most of it are group and you will always be the parasite of the group, then you never know about this. Okay. So in the full adder, we have the sum and the carry. We have the sum and the carry, which we can get this equation from this truth table. Either you get it from the truth table or you get it when you change it to KMAT. Same goes to this. Okay. Half adder, full adder, and this is the 2-level realization of the full adder. Okay. So we have the first level here and the second level here. Get the answer. The full adder needs 2 level. Oh, Nabila is not sleeping. Nabila cannot use mic. Okay. Right. Then we can have a full adder with a multi-level. So just now it's 2-level. Now it's multi-level. 3-level here. But with a hierarchical realization where this is actually the half adder block. We do the half adder first, and then as a module, and then you instantiate the module to make a full adder. You call the module to make a full adder. So this is the full adder schematic for a cascadable module. So you make a full adder module which is cascadable. Cascadable means you can connect this module with another full adder module. Cascade means to connect multiple same module, same thing. So we can cascade multiple full adder, make multiple bit adder, right? And this is the schematic. Adder with multi-level, first level, second, and third. Right? And then we have the orbit ripple carry adder that looks like this. You're supposed to know this. But there are problems with the 4-bit ripple carry adders. But there are problems with the 4-bit ripple carry adders. So who can tell me what is the problem? Maslah?
Yes, Doctor.
Yeah, can you think of a problem of the ripple carry adder?
C naught.
C naught. Okay, what about it?
Yeah, we need to have an already carry to start. But
You
sometimes
need to have carry.
Yeah,
Seems like you've done some reading. Okay. Yeah, that's true. The problem is with the carry basically. Okay, because here in the full adder we have three inputs, right? Which is input 1, input true, and input carry. Okay, input 1 and input 2, you can get it ready before we run the circuit. Okay, you already know you want to add 1 0 1 0 and 0 1 0 1. So this is your input 1 and this is your input 2, being that this is A0, A1, A2, A3, B0, B1, B2, B3. But where's our C? Okay, so Muhammad El Sayed here said the problem with the adder is the delay, which is correct. Okay, but the delay is due to the carry. Okay, the delay is due to the carry. Why? Because we don't have the carry at the beginning. We don't have the carry at the beginning of our our clock cycle. Beginning of our clock. We don't have the carry. We only have input A and input B. Okay. So to calculate using the ripple carry adder, we have C0. We have C0. So C0 is not a problem. C0, we have the it ready. Okay. But C1, C2, C3, which is the important input for this full adder. Okay. The consequence full adder. We cannot calculate S1 before we know what is C1. We cannot calculate S2 before we know what is C2, which is we cannot know if we don't know what is S1 and C1. Okay, and so on. So this is 4 bits. Okay. So to get the answer here, which is the S3, okay, we have to wait process the circuit to ripple. Imagine you are doing a 64-bit adder. Okay, 64-bit adder. Imagine how long you have to wait, okay, to get into the MSB, the sum. Right? So that is the problem with ripple carry adder. Looks like everyone understand this. Very good. Okay, so how can we improve the adder circuit? Okay, well, how can we improve the adder circuit? Okay, it is by designing a high-speed adder. Okay. Now, before that, delay of cascading adder. This is the schematic of the cascadable full adder. Okay. Now we're going to see the delay analysis of this, right? Okay. So we have done the propagation delay before. You can see that we have, let's say, the XOR is 2 tau. Okay, the XOR is 2 tau and the other AND and OR is tau. Okay, so why XOR is 2 tau? It's because XOR is 2 tau is because XOR is contained of N and OR. Okay. Contains of N and OR. So it's 2 tau, and the rest of N and OR is tau. So you can see that each path, especially this S, is 4 tau. Then this one is also 4 tau. This here is also 4 tau. Okay. And so on. You can see it here. You can see the path of from CI to get the next round C. Okay. Carry to the next round carry. Carry to the sum. Okay. Input to the carry, and input to the sum. Right? And if we have 4-bit ripple carry adder, we can divide we can do the analysis of the delay by dividing it to 3 stages. Okay? Which is from A here to T. This is supposed to be the stage 0, and this is supposed to be the intermediate stage, and this is the delay stage. Okay. So this is from A0 or B0 to C1. This is the first stage, and the second stage is from C1 until the last C, which is C n minus 1, where n is the number of bits, so we have 4 bits. So C3 here. Then the last stage is from C3 S3. So from A0 and B or B0 to C1 here. Any rubbish? From A0 or B0 to C1 here, from here to here, we have 40. So the number here is the accumulation after we go through all the gates. So XOR is 2 tau, and this is tau and tau, so we have 40. And then from C1 to C3, have 8, 2, and 4, 8. Okay. And then from C3, so we just calculate. 40, and then another 2T here for the last stage. So it's 40, 4 tau, plus the intermediate stage. Now, let me know if I'm wrong. Last stage is 6. But this is 10. 10 tau. Did I get that correct? That's the textbook, right? Everyone? Any objection? Everyone?
That's correct, Doctor.
Yeah, that's correct. Okay. Is it hard to follow? Hard to follow? Any questions so far?
No question for me.
No questions. Thank you. What about others? Is it hard to follow?
Doktor,
Yes.
tu maknanya yang dalam nota ni, yang pengiraan dia buat tu jangan ikut lah.
Mana? Nota mana? Nota ni?
Yang dalam,
Kenapa?
4 atau
N? N tolak 2. N tolak 2, 2. 2 darab 2, 4. So 4.
sekejap.
Tak?
Okey doktor.
N. Okay. So N is 4. 4 minus 2. Okay. For the intermediate stages, we have a formula for this, which is 2 multiplied N minus 2. Okay. So our N, which is the number of bit in this adder, is 4. So 4 minus 2 is 2. 2 by 2 is 4. So we got 4 bit, which is true. From C1, right? So 1, 2, 3, 40. And then the last stage, which is the C3 minus S3, that will be only 1 XOR, which means another 2 tau. Okay, I keep confusing T and tau. Please excuse me for that. Okay, so we can simplify this formula into this, where for the whole ripple carry adder, n bit ripple carry adder, this is only for ripple carry adder or n bit. The delay is 2n plus 2 tau. So here our n is 4. So 2n is 8 plus, then we got 10. Okay, 10 tau. So in big O notation, so this is actually not that important for you as an engineer. Big O notation is more important for a computer science student, but it's good to know. So in the big O notation, which is in the order of the computation, so the delay is linear with n, which is the number of bits. So how to write it in a big O notation? You write it as O, okay, big O, bracket n. Okay, big O bracket n. So this is a big O notation. So this means it is linear. The number of bits, linear with n. So if it's not linear, so we can write it as 1 over n, or if it's exponential, you can write it as square. So that is the how to write the big O notation, but it's not important. Just remember that for a ripple carry adder, so the delay is linear with the number of bits, or we can write it like this using the big O notation. Most importantly is how to calculate the delay of the ripple carry adder, because you can see, as you can see, is have questions that ask the path, okay, delay. This is carried using NAND gates. So they change the full adder. This is the full adder. They change the AND and OR here to become a NAND. This is a NAND, right? And then probably I think they change the value here, like it's not 2 tau. The delay of XOR is 3 tau and the other gate is 1 tau. So I mean the NAND is 1 tau. And then they ask you the critical path and what is the delay. So that kind of question will be in this one. Let's see this one. This one is carry look ahead adders and carry adders. So you have to know what is the carry look ahead adders and ripple carry adders delay, always given here. So you just have to calculate. And then this one. They are asking for delay analysis. So you have to understand how to see the delay, how to do the delay analysis. Moving on. Any questions? Any more questions? We can move to the next page. So here we are discussing about the ripple carry adder. But we are going to see problems in the, we have seen the problems in ripple carry adder and we're going to see how we can speed it up in the carry look ahead adder. Okay, carry look ahead adder, always known as CLA. Right? Okay. So this is a ripple, this full adder. So the carry look ahead adder will compute, okay, the sum. The sum. We want to know the sum, right? When we have an adder, we want to know the sum. What is the sum? Right? But to get the sum, we have to know what is the carry bit for each bit, right? So in the carry look ahead adder, we want to compute the sum faster than the ripple carry adder. And this adder, okay? So without waiting for the carry bit. So in ripple carry adder, we have to wait for the carry bit from the previous bit, okay, to add or to calculate the next bit. And we calculate the bit one by one. Okay. But actually, we can prepare the, we call this next higher bit, next higher position bit carry, because it's the carry of the higher position bit, okay, next higher position bit. Okay, we can calculate the next higher position bit carry at the start of the circuit. So before we run the circuit. So how can we do that? We have to do analysis of the behavior of the carry, okay, the carry behavior. So here, as we can see here, this is the full adder. So if both A and B is a 0, okay, regardless of C, so if C is 0 or C is 1, the next higher position bit carry will be 0, or we call it as carry kill. So no carry will be generated from this condition. Okay, when A is 0, B is 0, there will be no carry to bring to the next bit. Okay, right? Let's look at the first condition here. When A and B are both 1, in this, when A and B are both 1, regardless of the C here, so the next higher position of bit carry will be 1. We will generate a carry to propagate into the next bit. Right? We will generate carry to propagate into the next bit when A and B are both 1. And then when A is not equal to B, means it's whether A is 0, B is 1, or A is 1, B is 0. Okay. Like this condition, these 4 conditions. When the carry from the previous stage is 1, okay, we will generate the carry. So there are 4 conditions where we are going to generate the carry that will be propagated to the next bit, okay, to the next higher position bit, which is when both A and B is 1, or when either one is 1 and the carry in, okay, the previous stage carry is 1. Okay, remember that.
Doctor, what is BI and GI?
BI, here, GI and BI.
Yeah.
So the GI and PI is the carry generate. So that is the GI, and also the carry propagate, PI. So this condition here, the first condition here is for GI, because we're going to generate here. Regardless of the carry, at this stage, we will generate the carry just looking at the A and B. Okay. But the PI here, we will propagate the carry. Okay. We will, when A is not equal to B, we will propagate this carry from the carry from this stage to the next stage. See, back drawing, sorry. So we will just propagate, we will just bring along the carry from the previous stage to the next stage. If the previous stage carry is 0, we will propagate it to the next stage, the higher bit, so it will also be 0. If it's 1, it will be 1. We will just propagate the carry. Here, regardless of this, okay, when A and B is both equal to 1, regardless of this, we don't mind this, we will generate the carry. But here, when A is not equal to B, we will propagate the carry. Right? So, computer science people have think of the formula, okay, the mathematical formula for GI and PI, right? Which is GI is equal to AIBI, where I is the position of bit, and PI is equal to AI plus BI. Propagate the carry in to stage to the next stage. If the half sum is AI. So, any questions so far? Or did you get what I mean by GI and PI here?
Yes, probably it's the order that is given. If it's 0, 1, that means do not generate but propagate. If it's 1, 1, generate and propagate.
Yes, here.
Yeah, okay, I understand.
Right. And about why is this value is 1 and 0? Did you get it? Here is 0 and here is 1. Yeah?
Yes, I do.
Because, yeah, for the rest of the class, because G1, not G1, GI is AI, BI, and PI is AI plus PI. Right? Okay. Right? Because it will propagate. It's carry. Right? Now that brings us to the carry look ahead adder. Okay? So the carry look ahead adder is we want to calculate the next stage carry. The next stage carry using the C that we have and also A and B. Right? And we have the circuit for this is the partial full adder. Okay, partial full adder. Right? Okay. I hope everyone could follow about the carry look ahead adder. I'm just going to open a whiteboard here. Okay. Right, can you see can you see my whiteboard?
Yeah, yes,
Yes,
can.
yes. We can
Right,
see.
thank you. Okay, so in the ripple carry adder, so we have a ripple carry adder. Let's see about 4 bits, right? We have full adder, 4 full adder. The input is A and B, right? A, B, and then also C. Then the output is the sum and also the carry. C0, A0, B0, A0, B0, sorry, A1, B1, C1, A2, B2, AB3, and sum 0, sum 3, everything. Sum of next bit, which is carry to the next bit, which is carry 1, carry 2, and carry. So here the problem with the ripple carry adder is we cannot calculate this if we do not calculate this. We cannot calculate this if we do not calculate this. It has to wait. Okay, the next bit have to wait for the previous bit. So we don't want this. We don't want this in the carry look ahead adder. We don't want to wait. We want to wait previous carry. So hopefully you can find a way to calculate C1, C2, C3 here. In case of the 4-bit ripple iterative, we want to calculate C1, C2, C3 here without waiting, so that when we have input, let's say we want to calculate 1 0 1 0 and 0 1 0 1, and then we have the carry 0. So our initial input is A0, A1, A2, A3, and B0, B1, B2, B3, and also C0. So this is our initial input. This is what we know before we run the circuit. So we just want to use this value. Okay? We just want to use this value to calculate C1, C2, C3. So to do that, we have to add a circuit here. It's supposed to be like a cloud-like. Usually in the digital design system, combinational circuit is shown like in the cloud. I don't know why. Okay. So we want to add circuits. Add circuits means we add more gates into our circuits. Okay, remember I said at the beginning of the semester, when we design a digital system, okay, we care about 3 things. The power consumption, most important thing, the delay, and also the area of the circuit. Now, when we do this, when we design the carry loop ahead adder, okay, from the ripple carry adder, we want to reduce the delay, but we have to have a trade-off where we increase the area. We increase the area. We add gates here. We increase the area, but we reduce the delay. So what is this? Right? What is this? And these gates must be connected to inputs that we know from the beginning here. Hope you can follow that. Was good, everyone? Right. So, okay. Aminu, questions? No?
No questions, Doctor.
All right. So, okay, remember our P here is AI plus BI, and our G here is AI BI. Okay. So our carry here is CI plus 1 here is, if AI plus BI is 0, if AI plus BI is 0, we will follow GI. And if our AI plus BI is 1, so this is actually our PI, we will follow this is the CI plus 1. I C. Okay. So if we look into this, actually, CI plus 1 is AIBI plus AI plus EI. So this looks familiar to you? Familiar to you? Anyone? Does this look familiar to you? This is actually, go back, it's actually how we calculate the CI, okay, of our full adder. We just rename this as GI and this is the PI. Okay, so, well, if it's just the same as the full adder, then what's the improvement? You ask. We're not going anywhere yet. We're still here. The next carry adder, the next carry is actually same as the next carry calculated in the full adder. Okay, let's see. Is it a problem with you if I don't want to like show all the equations at once? Is it a problem with you if the equation is down here? Because I want to like close part of it. So is there any problem? I hope you can see it clear. Is it clear on your side? We're talking about this now.
Boleh nampak Doktor.
Alright, great. Nampak. Okay, so C0, we already know what is C0, right? Information is, A0 to A3, B0 to B3, and C0. We know what is C0. So from this information, we can calculate C1, okay? Because CI, okay, here CI is equal to GI plus PICI. So we can calculate C1. This is I minus 1. Oh, sorry. This one, CI plus 1 is AIBI plus AI plus BI plus CI, or CI plus 1. Okay, the next carry is GI plus PICI, right? So we can calculate C1, which is G0 plus P0 plus C0, right? So from here, we can also calculate C2, which is G1 plus P1 plus C1. Okay? But we don't want this. If we continue doing this, like the full adder, we have to wait. We have to wait C1 to be calculated to get C2. So what we do is we replace this C1 with this value, which is G0, P0, C0, that we know before we run the circuit. Okay? We know from the initial point, which is can get it like here. G1. We know G1? Yes, we do. G1 is A1, B1. We know from the beginning. P1, do we know P1? Yes, we do. P1 is A1 plus B1. We know that from the beginning. We have the information. And P1, P0, C0, Can we know that? Yes, because we have A1, B1, and C0, and also P0. Here is A0, B0. Okay, A0 plus B0. So, same goes to when we want to calculate C3. Okay, C3 is G2 plus P2 plus C2, but we want to eliminate this C2. So we replace that with this value that we know from the beginning. And same goes to C4. Same goes to C4. C4 is G3 plus P3 C3. Okay, we want to eliminate this, right? Substitute this. The value that we know from the beginning, from the initial point, right? So this is so when you expand this, you can expand it in many ways, but let's just expand this with our favorite form, which is the sum of product. Okay? This is sum of product, right? Don't leave it this way. Okay? Just make it a sum of product, so that you will have one level of sorry. Oh yeah, one level of N and another level. Oh, that's very bad. Another level of OR, right? Let's make it a sum of products. So you see, every single C equation here is a sum of product. So this is the circuit. The sum of product here will be, so here at this cloud, we will have the sum of product C1. Here we have the sum of product of C2. Here we have the sum of product of C3 that we can calculate, that we can have the value here, okay, before we start running the circuit. Everyone can follow? Everyone can follow?
Doctor, so
Yes.
we are replacing C1, C2, C3 in function of C0 since we already know it. Right?
Yes. Yes.
To make it faster.
Yes. Make it faster.
So isn't it like if we add more gate, it will become slower since like each gate has a delay?
Okay, let's see that. So let's do the design analysis for that. Ready? Yeah, we are. Oh, okay. Am I going to do this? So the G and P is calculated as like this. So let me think. A, you snip, snip, snip. Mm. I know how to do this. I understand your questions. Wait. I want it to be like this. Okay. Sorry to take some times. Another one. Right? This is T right? This I. Now we have this value, partial adder, and then also have for this all these gates, right? Written like this. Copy. Here. So this is in general. You see, I write it I and yeah, I'm using I here. But this is for each bit. So I only draw this once. So you understand that we have 4 of these for PT0, PT1, PT2, PT3. That is supposed to. This is called the partial full adder, isn't it? PFE. Okay, let me go back. It's called the partial full adder, PFE. So have a PFE here. Or PFE. Right. Can us follow? Everyone, you follow? Okay.
Yes, boy.
We have. Okay. So here, let's see how many level we have. So we have one level. Level is level 1, level 2. So in your PFA, you have 2 levels. In each of these, you also have 2 levels because we follow the SOP, right, class? We follow the SOP. I mean, we follow the sum of product rules when we expand the calculation equation. When we expand the calculation, we make it SOP. We follow the SOP. Okay, sum of product, so that we could have only 2 levels. Only 2 levels. Is level 1, level 2, level 3, and level 4 here. So we have 4 levels. So the time taken is only 5 t. here, we took 2t. Here, we took 2t, but this level is basically taking 1t. So in level 1, in 2t, level 2 is taking 1t. Don't worry about this. It is taking 2t, but we're not going to use S1, SI anywhere after this. Okay, this is the result that we want. So if it's taking, if it is taking 2 tau, means the timeline. We will get, so this is the first tau. Satu. Okay. 4, 5, sorry. Alright. So at this level, the first level here, we need 2 tau. So tau 1, tau 2. And here, at this level, we only need 1 tau. Okay, so that at the end of this, we could already have PI and GI, but SI is not finished yet. SI need 2 tau, so SI got here. But that will be no problem because we're not going to use SI in any other place. Right? And then here, at this level 3, we will run all these gates. And at level 4, we will run all these gates. So we only need 5 tau. 5 tau to get all the carry ready. And once we get all the carry ready, we can calculate all the S. Right? So that is much simpler. That is much simpler than the ripple carry adder, which took us 10 tau. Follow me, Anas? You understand what I'm saying?
Yeah, that's understood.
Okay, so that is how we improve the ripple carry adder. We improve the ripple carry adder using the carry look ahead adder, where we calculate the carry out, all the carry out, the equation beforehand. Okay?
Sensei,
Yes.
may I ask a question?
Yes.
Can you go to the whiteboard? I asked it there. You see A and B, the A and B will get OR and AND gate at the level 2, right? But it only take 1 tau, then level 3 you get 1 tau, level 4 will get 1 tau, not only 3 tau only. Why 5 tau? My question is that that you see at level 2 A and B is all AI plus BI, and the AND gate all get take only 1 tau, right?
1 tau.
And level 3 take 1 tau, level 4 take 1 tau. Then that means there's 3 tau only, right?
Okay. To
Then
calculate
should the longest one is 4 tau, is the sum 4 tau. So 3 tau and 4 tau, the longest is 4 tau. That should be the total time. Is it 4 tau or 5 tau? Yeah. My question is that.
Okay. Okay. So this is different from what is written in the textbook. I thought this would be like easier to understand, so I draw it like this. Okay, so to complete the carry, we only need what, 3 tau, 3 tau. Here 1 tau, 2 tau, 3 tau. Okay, but to get all the S, to get all the all the sum, we need 5 tau. Because while we calculate the 3 tau, we also calculate the S, which is additional here. This is another XOR.
Isn't it that 4 is 4 tau only? 2 tau, 2 tau, not 4 tau. Yeah, the XOR gate is 4 tau, 2 tau, 2 tau, then
this is at the same level as this.
4 tau.
This is at the same level of this. So we just calculate like this. So this is 2 tau. We calculate the S, we have to start from this level, right? So at this level, we only calculate. Now we have 2 tau here. At this level, while calculating the GI and PI, we also have started calculating the SI together.
Yeah.
Yeah, it's on the same level.
2 tau, 2 tau.
So now this is taking 2 tau. So here at the T4 here, right? T4 here, because the first level you took 2 tau, and then the next level, the second level, you have already reached 3 tau, and then at the fourth tau here, at 4 tau here, okay, you already get GI and PI, but you haven't got the SI. SI only can be calculated here at the 5th tau, because it's 2 tau. So this is 1 tau, this is another tau. So it's 2 tau.
I think I get it.
Because this is at the same level. To calculate GI, PI, and SI. Only that we don't get the SI here. SI is here. SI can be obtained here.
But why the GI and PI that get N and O get cannot be at the first level? Yeah, why?
Why GI? Oh, okay. You can write it at the first
get and
level.
O get.
So you can write it here, but I want to make this T1 and 2. I want to make this 2 tau. So it's quite confusing. You can choose either way.
Yeah.
But the total is 5 tau. Okay, let's see what the textbook says. So the textbook explain this in a different way. Okay, and can we go there first?
Okay.
This is
sorry.
no,
sorry.
you don't have to say sorry. Okay, you don't have to say sorry. So this is our carry look ahead adder. Okay, from A0 to G0. So this slide is more confusing probably. For me it is confusing. Might be easier for you to understand. So this first tau is to get PI and GI, we need tau. Get this. Then to calculate all C until C4, okay, from C0, we substitute it in the equation. Have C0 at the beginning, and we can calculate all these C4. That is 2 tau. 2 tau. Okay. Maybe this is easier for you, don't you think? So to get PI and GI, because PI is only one all, right? PI. And GI is only, one N, right? So at the same level. So it's tau. Tau. It's tau. To get C4 from C0, we calculate C4 using C0. Not C4 lah, I mean C1 to C4. To calculate C1 to C4 means C1, C2, C3, C4 using C0. Okay, we substitute C0, use C0. That is another 2 tau. 1 tau at this level, another tau at this level. So that is 2 tau. Now the problem is to get C3 from S3. C3 from S3. Here we have C3, S3. This is 2 tau. Because you only go through 1 XOR. What about this? This is not tau because it is at the same level as this stage. As the previous stage lah, it doesn't matter whether it's this stage or this stage. So we don't count this. The previous stage. Get C3 from S3, to get S3 from C3, we only go through 1 XOR. Only 1 XOR. Is that easier to understand?
I think I get it, but I later study back.
Okay.
Yeah.
Okay. If you have question after this, you can still ask in the group. Right.
Okay, thank you, Sensei.
Okay. So, basically, the 1 carry look ahead generator for 4-bit. We have delay, the total delay of 5 tau. 5 tau. Can everyone follow? Is the class is too heavy? Maybe you still need to check it later. Right? Okay. And let me see. Oh, okay. About the fan out. So here, okay. Now is 9:42. Just a little bit more. Okay, just a little bit more. So we can go as far as we can, as many bits as we can, right? So how do you say this? The longer we go, the longer bit we go, because we want to maintain this as 2 tau. Okay. The carry look ahead generator, which is the circuit that calculate all the carry, we want to maintain it to be 2 tau, 2 level, 2 stages. Okay. But to maintain these 2 stages, we have a limitation, right? What are the limitation? What is the limitation? Can we put, see, if we want to calculate 4-bit, here eventually at C4, we have to put 4, good Elias, Muhammad Elias, El Sayed, sorry. We have to put 5 input into our OR gate, okay? But we have this limitation of number of input that is coming into our OR gates. Okay, the longer number of bit, okay, we have more wire coming into our OR gate, but we have the limitation, and the limitation is called as. Can anyone remember? What is it called? And it's not only the last OR gate; it's also burden the other gates too. Yeah, we can do two wire, 3 wire, 2 input, 3 input, 4 input. Anyone knows what are the limitation codes? Nuria Hanim. Nuria Hanim, you here? Nuria Hanim? Not here? Might need one to wake up because it's almost 10. Tanshini? Tanshini? Can you tell me what are the limitation codes?
Yes.
What do we call this? We cannot have a lot of input coming into the OR.
Not sure.
Okay.
Maybe I forgot
Not
it.
sure.
Got tips.
Yeah, you forgot it. Maybe you forgot it. It's something something with a fan. Is it fan in
Fan out.
or fan out? Fan out? Is it?
Yeah.
So it's actually a fan in because it's input, right? We cannot have a lot of input here. That's a fan in problem. So what are the limitation of regular gates? It's around 6 to 8. So like probably you can have like the current CMOS gates now, probably you can pass up to 8 inputs. I'm not sure about this. We have to check again. Okay, up to 8 inputs. So how can we do 16-bit adder if we can only have 8 inputs coming into our XOR? But this, we have 8. We can have 8 inputs coming, like the most inputs that can have coming into our OR gate here is probably 8. But of course, there will be like a difference in each supplier of the gates, and of course, there will be other risk. Okay, fan-in risk. Okay, we don't want that. So instead of making a lot of inputs into the OR gates, okay, we opt to have a block of 4-bit carry look head adder. We have 4-bit carry look head adder block. So when we want to do a 12-bit adder using a carry look head adder, we use 3 block. Okay, 3 block of carry look head adder. So the delay, if you want to calculate, generate PI and GI, that is tau, same tau, because they are at the same level. And then to generate CI, MSB, the carry at the MSB, we have to multiply 2T. So each block need 2T, 2 tau, sorry. Each block need 2 tau. So we have 3 blocks here, means we need to multiply that with the number of blocks. M here is the number of blocks. And so why we need to multiply that? Because at the second block here, we have to know what is C4. We have to know what is C4 before we can calculate. So we have to wait 2 tau and then we can calculate this. And we wait another 2 tau to get C8 and we can calculate this. So the total, this is 2 tau. 2 tau. The total to calculate from, calculate all the C, okay, C1 to C12, okay, using C0, we need 6 tau, which is the number of block multiplied with 2 tau, because each block needs 2 tau, right? And then the final sum here, from here to here, is sum at bit 11. We need another 2 tau from that XOR. So the total will be calculated as 1 plus 2m plus 2 tau, or we say 2m plus 3 tau. So for this architecture of carry look ahead adder, where we only cascade the 4-bit carry look ahead adder, the delay is calculated using this formula, 2m plus 3. So here we have 3 block. So our delay is 2 by 3, 6 is 9. Okay. So in your test questions, probably they will calculate 16-bit cascaded carry look ahead. So we have another 4-bit here. And the delay will be, so if we have 4 block of 4-bit carry look ahead adder, the delay will be, so this is the symbol for the, yeah, this is the symbol for delay.
4.
Okay. 4 block plus
3.
is 8 plus 3, 11. 11 tau. Okay. But can we improve this? Yes, we can. Okay. By doing the hierarchical carry look ahead adder. Hierarchical carry look ahead adder. And we will see this next week. Okay. I think you have enough today. You have learned about the carry look ahead adder, and you understand about how to calculate the delay, and what if we have a bigger circuit? Okay, instead of 4-bit, we have 12 bits or probably 16-bit, but that is still a lot. It is 11 tau. We want to improve this, so you can read the textbook or read any other reference book about the hierarchical carry look ahead adder. So how can we improve the calculation in the block? It's called the CLA with the prime here. Okay. So that for 16-bit adder, so instead of 11 that we count just now, that we calculate just now, we can get only 9 tau. Okay, this is what we're going to see on testing. 9 tau. And then, what if we have other type of adder, which is the carry select adder? So in the carry select adder, we are using 3 4-bit adder. We are using 3 4-bit adder, and there is the formula for the total delay. But inside here, inside the 4-bit adder, we can design it using a different 4-bit adder. Probably here we want to use the carry adder. But here we just want to use the ripple carry adder. Remember, our design must be optimized considering the power, area, and delay. Okay. If we only want to focus on the delay, we want a small delay, we can use all small delay of adder circuit in 3 of these. But if you are also considering the area, maybe we can trade off one of these with a ripple carry adder, because that is very simple, although it takes a lot of time, a long time. The delay is big. And we will learn about the carry safe adder, but only like the intro, not going to really look into it. And we will learn how to do, like, to see different architecture of the carry safe adder, okay, how it will affect the delay. Okay, if we sort the block differently, we will get different delay. Okay, so we will see this next Thursday, and then we will continue with the subtractor, which is basically the adder. It's basically the adder, but it's a complement. So before we stop, okay, remember the arithmetic circuit is adder, subtractor, multiplier, divider. That's the example of the arithmetic circuits. But adder is the most arithmetic circuit. So, like, if you one day become a designer, make sure you try to the most optimized adder. Why? Because the subtractor is made of adder. We implement the adder circuit in the subtractor. Same goes to the multiplier. We use adder circuit in the multiplier. We just add it how many times we want, right? That's how we multiply. Divider, we are using the sub, but the sub is using the add. So which means we also are using the adder. So that is why you will see a lot of adder circuit, okay, being researched. Once we got a good adder circuit, we could have a good multiplier, divider, and subtractor. So today we have done the carry look ahead adder. What can you say, before we finish? What can you say about the carry look ahead adder? If I ask you, what is a carry look ahead adder? Yap Shin Chin.
Yes, doctor.
Okay, what can you say about the carry look ahead adder that we learned today?
Carry adder has carry in and carry out.
Full adder also have carry in and carry out.
Carry adder.
What do you think? Any other thoughts on the carry look ahead adder?
Carry look ahead adder is the faster version of full adder.
Carry look ahead adder is the faster version of full adder. Okay, carry look ahead adder is a faster version of look ahead adder, but we trade off. What do we trade off?
With the area?
Area. Very good. Okay, we trade off the area. We put more bits into the circuit. Sorry, not bits. We put more gates into the circuit to get a faster calculation, okay, to reduce the delay. So that is the carry look ahead adder. You can say that. Okay, what is the carry look ahead adder? Carry look ahead adder is an improvement of the ripple carry adder in terms of delay. We improve the delay, but we trade it off. We trade off the delay with the area. We have to add area to the circuit. Okay, I guess you have class after this, so see you again next Thursday, probably same time, 8:15. Okay?
Doctor,
Yes,
I ask
questions?
a question? Yeah. When will be the actual date of submission milestone 2?
Mission of?
The actual date of submission milestone 2.
Oh, milestone 2. I will check and let you know in the WhatsApp after this.
Okay, so in
Because I
milestone 2 we
forgot.
have to make a video only.
I will let you know also about that. Right? Oh yeah, I should have. So next on Thursday or probably earlier, I will brief about the milestone 2. I will give briefing about the milestone 2. Okay?
Okay.
Remind me at the
Doctor,
beginning of the class, Anas. Sorry. Yes, is it? What is it?
I also got a problem with my quarters.
Quarters, okay.
Maybe missing of the mega wizard. What yeah.
Oh, okay.
My
Mega
version,
Visit.
I don't know why it is missing that. Yeah, that
What
mega
version are you
wizard.
using?
So I don't know.
Which version?
14.1.
14.1 have the mega. What is it? Mega. It's in the tools, under tools. Then you can see the IP library, and then you can check the circuit that you want, the IC that you want, and then there will be like the mega wizard. No?
Oh, yesterday I found I go and search already. Also don't have. Yeah. My
The whole
friend
thing,
also using the same. Yeah, same.
14.1. Okay. Because
Yeah, my
I
Honey Kim
see it
using this version.
really because I talked to the other lecturer that is using 14.1. It seems like she has no problems with the mega wizard. Probably you can
Reinstall it.
yeah,
Is it?
reinstall. Yeah, if you cannot find it, maybe you can like send me a short video on you trying to find it, but you cannot find.
Mm.
Okay, maybe you can do that first.
Yeah. Okay.
Okay. Just send in the group so that everyone can see the problem.
Okay.
All right. So it's 10:01 a.m. now. Sorry if you have class after this. You can